Good morning, students. Our today's topic is solution by spherical means. So first of all, we discuss notations related to averages over certain spheres. So let us take a point x belonging to n-dimensional real Euclidean space, t for time, which is positive, and r greater than 0, which is for the radius of the sphere. We define capital U as the average of the function small u over the sphere with center x and radius r. So this is the average of function u over this sphere. Here x is fixed, r and t, these are the variables. So we can say that this function capital U, that is a function of r and t. Second notation, capital G, which is the average of the function small g over the sphere with center x and radius r. Third notation, capital H, which is the average of the function small h over the sphere with center x, radius r. Now, next we prove the result for the solution of initial value problem, which is satisfied by this function capital U. And this is given by Euler Poisson Darboux equation. The statement for this theorem is, we fix a point x belonging to n-dimensional real Euclidean space. N is greater than or equal to 2. And let us take m is also greater than or equal to 2 and a function u, which is m times continuously differentiable function on the space Rn cross semi-open interval 0 to infinity. This function u satisfies the initial value problem for the wave equation. Wave equation is given by curl to u by curl t2 minus Laplacian of u is equal to 0 in the space Rn cross open interval 0 to infinity. The initial conditions are, when time is 0, the value of function u is g and the value of partial derivative of u is h. These are the initial conditions. We are to prove that the function capital U, which we defined as the average of the function small u over the sphere with center x, radius r. We are to prove that this u is m times continuously differentiable on the closure of positive real line cross semi-open interval 0 to infinity. And we are to prove that u solves the partial differential equation curl to u by curl t2 minus curl to u by curl r2 minus n minus 1 upon r into curl u by curl r is equal to 0 in the space r plus cross open interval 0 to infinity. With the initial conditions, the value of this function is g when time is 0 and its partial derivative with respect to t, that is h. So this partial differential equation, that is called Euler Poisson Darboux equation. So let us prove that the function u satisfies this partial differential equation. So let us find the partial derivative of function u with respect to r. Now by definition, this function u, that is the average of the function small u over the sphere with center x, radius r. Now because we are to differentiate this function u with respect to the radius of sphere, and we cannot directly differentiate a function with respect to the radius of sphere. So first of all, we will have to convert this sphere into a unit sphere. So let us make a substitution. Y is equal to x plus rz. From here, the value of z will be y minus x upon r. Therefore, z mod, that will become the mod of y minus x upon r. Now, the distance of y from the center of the sphere, that is equal to radius. So, y minus x mod is equal to r. So, z mod is equal to 1. Means z is a point lying on a unit sphere. So correspondingly, we have the value of function u is now average value over the unit sphere of the function u. Inside, the value of y is x plus rz. So differentiating this function partially with respect to r. Here, the derivative of this function, that is given by du dot z. Du means gradient of u. Substituting the value of z again, this will again be converted into the sphere with center x, radius r, and correspondingly this point will again change into y, which will lie on the sphere with center x, radius r. Now y minus x upon r, this is a unit normal vector. Let us denote it by nu. So the partial derivative of u with respect to r is equal to average value of du dot nu over the sphere with center x, radius r. Now du dot nu, this is the directional derivative of u. By definition, it is given by curl u by curl nu. So partial derivative of u with respect to r is equal to average value of curl u by curl nu over the sphere with center x, radius r. Now let us convert this average integral into the simple integral by dividing by the surface area of the sphere. Now surface area of the sphere is given by n, alpha n, radius raised to the power n minus 1. So we have converted the average integral into the simple integral. Now let us apply Green's formula to convert this integral over a sphere into the ball with center x, radius r. So by Green's formula, integral of curl u by curl nu over this sphere, that will be integral of Laplacian of u over the ball with center x, radius r. Now let us again convert this integral into average integral by multiplying with the volume of this ball. Volume of this ball is given by alpha n into radius raised to the power n. Alpha n is cancelled out, so we are left with curl u by curl r is equal to r by n into average of Laplacian of u over the ball with center x, radius r. And as r approaches to 0, the limit of this function, that will be 0. Now let us find the second order partial derivative of function u with respect to r. So here we can use product rule. This is first function, this is second function. The derivative of first function r by n, that will be 1 by n, second function as it is, plus second function r by n as it is, derivative of this function with respect to r. Now this can further be written as 1 upon n, average value of Laplacian of u over the ball with center x, radius r. And in this term, we have converted this average integral into simple integral by dividing with the volume of the ball. Volume of the ball is alpha n, radius raised to the power n. Now this term we have taken as it is, and here because we are to find the derivative of this expression with respect to r, so we will use product rule. The derivative of this term, that will be minus n upon alpha n r raised to the power n plus 1, this term as it is, plus this term as it is, and the derivative of this integral with respect to r. Now from here, curl to u by curl r2 is equal to minus 1 by n into average of Laplacian of u over the ball with center x, radius r. This term we have taken as it is, and in this term we will use the formula for derivative of a function over a ball, that will be converted into the integral of function over the sphere. So let us simplify the last term in this expression by using this formula. Derivative of integral of a function over a ball with center x naught, radius r, that is given by the integral of the function over the sphere with center x naught and radius r. So we have used this formula in the last term. So correspondingly, we have obtained the second order partial derivative of function u with respect to r, which is given by 1 upon n into average of Laplacian of u over the ball with center x, radius r, minus average of Laplacian of u over the ball with center x, radius r. And the last term that we again have converted into average. So that is the average integral of Laplacian of u over the sphere with center x, radius r. Now let us apply the limits as r approaches to 0, both sides. So as r approaches to the 0, this ball will shrink to just a point, center. So the average value over the ball, that will become the value at the center of the ball. So this will be Laplacian of u at xt. In the same way here, as the radius approaches to 0, the ball will shrink to the center only. So this will become Laplacian of u at xt. So this term and this term are cancelled out. These two terms are cancelled out. So we are left with 1 upon n into Laplacian of u at xt. So we have obtained the second order partial derivative of function u with respect to r, and we have obtained its limit. Similarly, we can find the higher order derivatives of function u with respect to r, and we can see that u is m times continuously differentiable on r closure plus cross semi-open interval 0 to infinity. So this proves the first part. Now next we are to prove that the function capital U that satisfies the partial differential equation, which we have named as Euler Poisson Darboux equation. To prove that, let us find the value curl u by curl r. Curl u by curl r we have already obtained, which is r by n into 1 upon alpha n radius raised to the power n into integral of Laplacian of u over the ball. From here r will be cancelled with r raised to the power n. So in the denominator we have r raised to the power n minus 1. Now let us multiply both sides by r raised to the power n minus 1. So left side becomes r raised to the power n minus 1 into curl u by curl r. On the right side we have 1 upon n alpha n integral of Laplacian of u over the ball with center x, radius r. Now let us differentiate both sides with respect to r. So here by using product rule, first function as it is, derivative of this function with respect to r, that will become curl to u by curl r2, plus this function as it is, derivative of this term, that will be n minus 1 into r is to the power n minus 2. Here this is constant, derivative of this integral with respect to r, again by using the same formula which we discussed, derivative of integral of a function with respect to the radius of a ball, that will be same as the integral of the function over the sphere. So we have used that formula here. Now from here r is to the power n minus 1 into curl to u by curl r2 plus n minus 1 into r is to the power n minus 2 into curl u by curl r. is equal to 1 upon n alpha n into, now because Laplacian of u is equal to curl to u by curl u2, because small u is the function of the solution of the wave equation. So from there we can put the value of Laplacian of u here. So this can further be written as r is to the power n minus 1 into curl to u by curl r2 plus n minus 1 into r is to the power n minus 2 into curl u by curl r is equal to 1 upon n alpha n. We have converted this integral into the average integral by multiplying with the surface area of this sphere, which is n alpha n radius raised to the power n minus 1. So n alpha n will be cancelled out on the right side. So right side becomes r is to the power n minus 1 into average of curl to u by curl t2 over the sphere with center x, radius r. Now we will have to substitute the value of this average integral. For this we use this notation which we already defined, capital U as the average of the small u over the sphere with center x, radius r. So differentiating both sides partially with respect to t 2 times. So this will become curl to u by curl t2. On the right side we get average integral of curl to u by curl t2. Here u is small over the sphere with center x, radius r. Now we can substitute this value here. So we get the partial differential equation curl to u by curl r2 plus n minus 1 upon r into curl u by curl r is equal to curl to u by curl t2. So this is the required partial differential equation which is known as Euler Poisson Darboux equation. Now it remains to prove that when time is 0, the value of this function capital U, that is capital G, which is the average of the function small g over the sphere with center x, radius r. To verify the initial conditions, let us use this definition of average of small u, substituting t is equal to 0 here. So this equation becomes the value of capital U at x r 0. This is average of the function u, small u, at corresponding to t is equal to 0. When t is 0, we are given that the value of function u, that is g. So this becomes average of the function g over the sphere with center x, radius r. And according to the notations which we defined in the starting, this is capital G at xr. So we have proved one of the initial conditions. Now to check the second initial condition, let us differentiate here partially with respect to t. So left side will become curl u by curl t, and the right side we have average integral of curl u by curl t over this sphere with center x, radius r. Now let us put t is equal to 0 here. So on the right hand side we have the average integral of curl u by curl t at the point y comma 0, and we are given in the statement when time coordinate is 0, curl u by curl t, that is h. So this will become the average of the function small h over the sphere with center x, radius r. And according to the notations which we discussed, this is denoted by capital H at the point xr. So we have proved the Euler Poisson Darboux equation, curl to u by curl t2 minus curl to u by curl r2 minus n minus 1 upon r into curl u by curl r is equal to 0 in the space r plus cross semi-open interval, open interval 0 to infinity, with the initial conditions corresponding to time is equal to 0, the value of capital U is g, and the value of its partial derivative with respect to time t, that is h. So this completes the topic Euler Poisson Darboux equation.